Today I'm going to talk about 2 or 3 areas which have become particularly relevant in the context of power markets. In fact, I would say that the research in this area has been directly motivated by problems that have arisen in power markets. And let me just write this out. So, and I'm going to look at 3 of these problem classes today. The first of these is generalized Nash games. The second is a special class of generalized Nash games, which is, or actually I should just say that here, with and without shared constraints. The second is Stackelberg equilibria and MPEX, which is a generalization of a non-convex nonlinear program. Okay? And the third will in some sense combine the 2 of these, and we look at a class of games called multi-leader, multi-follow. Okay, so you've got a fair amount to cover. And so let's start with generalized Nash games. So in the context of generalized Nash games, and I gave you an overview of how these games emerge yesterday. So in a generalized Nash game, distinct from what you saw in the case of pure Nash games, you have this requirement here. Xi is dependent on what his or her competitors do in terms of the strategies. Where does that show up? So for instance, if you had a situation where this is a simple case, so this is a Cournot game where you have, so if I imposed a requirement that x1 xi plus x minus I had to satisfy could not be greater than some level d, right? So that's a very special class of that mapping. Okay, so whenever I write this mapping, you should be thinking how to take that mapping, how to take this constraint and transcribe it as that. So xi of x minus I. So I want to make sure everybody understands what they see when they. So remember in the past you had xi and xi. So this is a fixed set. So regardless of what, so if you have two agents competing, Vladimir and Alfea, if you make decisions, Alfea's decision does not affect the feasible space that Vladimir faces. Okay. On the other hand, xi of x minus I, for every x minus I, it produces a new set. Okay. The image is a set, not a vector. Sorry, not a constant set, but a set that is dependent on the choice of x minus I. So it's the set of xi such that xi plus x minus I is less than c, or whatever, less than d, or whatever it was. Okay. Now, if you notice in this case, this constraint is a common constraint for all players. Now you can change that. Suppose I said that you only have that this is dependent on some ci, which is, and I could say that you have something like this. Okay. Now this is idiosyncratic to player I, right? Player J will face a different constraint, slightly different. Xj of x minus j is going to be the set of xj such that 2xj plus x minus j is less than cj. Okay. So you could have different sets, different requirements. Okay. And as a consequence, we attach the qualifier generalized to distinguish this class of Nash games from standard Nash games where the strategy sets are invariant with the decisions of a particular agent's competitors. Okay. Now, so does everybody understand the distinction in terms of the models? Whenever you have any kind of coupling, the game essentially becomes a generalized Nash game. Now, you can do a variety of things to get rid of this in some partial fashion by relaxing it. Okay, so when you relax it, you obviously gotten rid of it, but then you need to deal with this multiplier that comes from relaxing this constraint. And somehow this multiplier has to be updated or specified in some way. Okay. But in the absence of such a relaxation, what you have corresponding to this, so given x minus I, if so generally we assume, right, at least in this context, because we are adhering to the requirements of convexity, that xi, now I want to make sure you can read what I mean, you can understand what I've written here. Xi is a mapping. It's not a set anymore, it's a mapping. It maps from r minus I to rin, but it's actually, I should have two arrows here. Sometimes to specify this, you put a double arrow to show that the image is no longer, it's essentially a set. So this is a set. And so, the two maps here, but this is a closed and convex valued, and I should have set valued map here. For some reason something happened. Convex valued, set valued map. So the image is a set. Okay. Now, as opposed to in general, what happens? In general, you can represent the pure Nash game as a generalized Nash game by specifying xi of x minus I is equal to just a set x bar I for all I. So then you have a pure Nash game, right, where you do not have shared constraints. Now, if you have convexity and continuous differentiability in xi for every x minus I, then given an x minus I, this problem is just a convex optimization problem. It doesn't differ in any structural fashion from the problems we've seen thus far. Okay, Farzana, do you see that? So if you don't see any distinctions, then we can write necessary and sufficient conditions as a variational inequality, right? And that variational inequality is the standard one where you have y minus xi transpose, the gradient in xi for all yi in this set. Now remember, for a given x minus I, xi of x minus I does not change. It's an invariant set. Okay, Carla, is that clear? Okay, so having said that, but when you write down the equilibrium conditions for all of the agents and bring them together, what you're left with is that sequence of variational inequalities, or that set of variational inequalities. Now they're all parameterized, but put together, what you notice is that no longer do you have the freedom, this set is no longer a fixed set, because the x minus I is being specified through other systems of variational inequalities. Okay, so remember, prior to this we had just x1 to xn, but now we have this parameterization, and this parameterization significantly complicates the issue. Okay, so I want to make sure that I didn't miss anything, but I want to make sure that I specify something in this. So this collection of coupled parameterized variational inequality problems is equivalent to the following quasi-variational inequality problem, or QVI. So the QVI, and this is important to note, the way I've stated it, there's one small thing that I need to just make sure everybody sees. The QVI problem, QVI x comma f requires, so I didn't mention this, requires an x in x of x. So last time, remember, for a VI, it was just x in a set, capital X, which was the Cartesian product of sets. So this is x lying in x of x. So you need a fixed point of this map such that y minus x so the x is the same and x of x is the Cartesian product of xi x minus I. Okay. So this, as you can see, this one change makes the problem significantly harder. Okay, it makes it significantly harder. So does everybody see why this requires you to find, in essence, it requires you to solve, in essence, a constrained fixed point problem. So I want a fixed point of capital X such that that fixed point satisfies this inequality for all y. Okay? So you can imagine how challenging this problem is. You want a fixed point that satisfies some other condition. Okay? So that gives you an indication of how nasty a problem we're dealing with. Okay? Now, a natural question is, are there simple existence statements for this kind of problem? And it turns out that there are, but you have to work a little on it. So let me show you actually I put them in an order which later on when I was walking I realized should have been switched, because I think this is an easier problem too. So consider QVI XF. So what was can someone remind me, what was the simplest requirement that we invoked for claiming existence to Vi x comma f? What was the simplest requirement? Do you guys remember?
Continuous map.
Continuous mapping. What did we require on the set? Convex. What else? And one more, right? Bounded, right? So you needed closed, bounded, non-empty, we just take for granted. But yes, non-empty, closed, convex, and bounded, right? So we need compactness, right? So in that setting, all that you need is essentially that the mapping F is continuous and single valued. Okay. Now, if you have a QVI, what you need is that the images of X, capital X, lie. So remember what the image is. For every X, X of X provides, so just to give you a pictorial representation of that, so X maps onto, little x, where little x is maybe Rn, and gives you another set. Okay? And as you change the points here, these sets keep changing. Right? What you need is, as long as if this set lies in a compact set, the image should also lie in a compact set. Okay? And in fact, that compact set should be convex and non-empty, of course. Okay? So what you need, so suppose, let me try and make that a little more precise, or not precise, provide you with a physical understanding of what that means. Suppose I told you that you're working in the context of power markets, and your X represents generation levels. Now your generation levels are immediately bounded by the aggregate capacity, right? So you know that they lie in some compact set. Based on that, if this image, X of capital X, can be shown to also lie in some other compact set, then, or in a similar compact set, identically specified compact set, gamma, then this requirement, assumption 1, is guaranteed. X has to be a non-empty, continuous, closed, and convex valued mapping on gamma. So that's not always the case, right? I could have this as the requirement. Xi of x minus I could be defined as a set of xi such that 3xi squared plus 4xi x2 squared is greater than 8. Now, is this set convex or concave? Well, not concave. You don't say concave sets. I mean, is it convex or not? Right? Is it? So what is this set? It looks like what? It's not a circle, right? Not the circle, what is it? But not the circle, the ellipse. Something at the ellipse, right? So it's outside, right? So you can clearly see that you have a lack of convexity here, right? So it's not true. Yeah? So just because you get some sort of shared constraint or coupled constraint, it's not always going to work. You have to be quite careful regarding what x of x produces. If it produces a non-convex set, you're already in trouble. Okay? So you want to be careful. These assumptions are quite restrictive. We don't have a choice. But in some sense, when you compare them with Vi of xf, they're not much more so, right? Because in Vi of xf, we also required that the set capital X be closed and convex. And all that we're requiring here is something similar, right? You cannot expect that these images be non-convex when the Vi, which was supposedly a simpler problem, could only be specified for convex sets. I mean, a solution of that, or sufficiency conditions for Vi of xf. So it's quite, it's not surprising that here the requirements are no longer, they're a little more stringent, but clearly it doesn't allow for non-convexity even in this case. So this result was first presented by Patrick Harker. Okay, so and under these conditions, what you have is that QVI, this should be x, comma f has a solution. Okay, so this is the first result under compactness. Now there's a weaker statement that you can provide, just as we provided one using coercivity here. So if I can generate, or if I can find a bounded open set U and a vector xref such that the following hold. Okay, so again I've used k and I should really have used x. I've moved between k and x. So we should just keep this as x. Okay, I try to change it wherever I saw it, but some places I've missed it. Okay, so there are some extra requirements here. The first requirement is that this set x of x bar is non-empty, and you have some, for any sequence, so for what you need to show is that these images converge in some set valued sense to x of x bar. So you need to make that assumption. So it's like a well-behavedness requirement on the set valued map. Okay. In most cases that you'll be working with, that assumption should generally hold. Xref has to lie in k of x for every x in the closure of the set U. Okay. And you remember we had this set L less than x comma f that we had used for Vi xref. A similar set comes out here, but instead of capital X just being a constant set, it's now a set valued map. Okay. So for this, if you can show that this intersection, the boundary of U is empty, then you can show that QVI x comma f has a solution. Okay, so this is a somewhat more elaborate requirement. So, and you can see that either of these problems is not that easy to analyze, right? So it's going to be harder than VIXF. But what I wanted to provide you with is at least a statement. And if you need, there are other results. There are other results that you can go and check on. Some of which are maybe slightly weaker, but not much weaker. In fact, the compactness one that I have on the next page by Harker is among the more stronger requirements. So when I say stronger, what I mean is the assumptions are more stringent. Okay. Okay. Questions? Okay. Yeah.
Maybe. In slide 5, could you please explain again how we can check mathematically that x has a convex value of the math outcome?
Yeah. So.
If you like to do one.
So in terms of the first thing is that you need to check if for any x, if you can show that the set is convex valued. So for instance, if you have xi of x minus I, right, and if I tell you that you can write this as xi such that g of xi x minus I less than 0. If I tell you that g is a convex function in xi given x minus I, then this set is always induced as convex. How do you prove that? Not difficult. The way you prove that is you would say G of lambda. So how do you prove that a set is convex? Well, take 2 points in the set, let's call them U and V, right? And you need to show that the convex combination lambda U plus 1 minus lambda V, suppose you take these two lying in xi of x minus I, which implies that G of U x minus I is less than 0 and G of V of x minus I is less than or equal to 0. Do you agree? If they lie in this set, then they have to satisfy this inequality. Right? So then you take the convex combination, which is G of this comma x minus I. By convexity of the function, you have lambda of G U x minus I plus 1 minus lambda of G of V x minus I. Each of these is less than or equal to 0, right? Which implies that the whole thing is going to be less than 0. Okay, so, but we're not done. We have to first show that this is convex. Then we have to show that suppose X, the overall set X lies in, so for all X in some compact set, I need to show that this image lies in that same set. So that you'll just have to, explicitly show a bound.
Okay, so you're saying that if for given rival decisions, if HM has a convex problem, and also, I don't know, the sets are compact,
Yeah.
then we have a solution.
Then we have a solution. But so let me just make sure that it's not, convexity is not enough. You need to have statement 1. What statement 1 says is that the image is not just convex valued, it's compact as well. And the size of that set can't be arbitrarily large. So if I told you the original decisions lie in some compact set, the images also have to lie in that compact set. Right? So what, if you think about where we are going with this, just to give you an idea, you remember in Brouwer's fixed point theorem, we had this thing where phi maps from C to C. Right? So when you have a mapping like this, it goes from one set to another set. Right? That's phi. So here what happens, you have something similar. The image has to be in a set which is bounded by the original set. So you can't, convexity of the image is not enough. You need it to be compact and you can't have an arbitrarily large set. Okay.
If you remember, we were talking about the contract decision that might be unbounded.
Okay. So if you have a contracting decision, well, of course, you could use some budgetary requirements to impose it, but if you don't, then this avenue is going to be hard for you.
But the previous one may work.
The previous one may well work, because in the previous one, I have no requirement on the set being compact. What I do require is require some continuity properties on the set. So if I take X from X bar, these images should not be changing very drastically. And that I think you should get, it should be induced by some continuity requirements on this.
And this is the one proved by Harker? Or
No, Harker is the next one. This one is a more general result. I'm not sure if this was proved by Jiangxi or somebody else. I don't know. I mean, the Harker's result is well known only because it was one of the first few results in this area. Okay. And this result is a bit like, and there's a coercivity variant of this as well, where this is also coercivity type result, but there's there's another one, but I didn't put all of them. There's a whole laundry.
This is the generic QVI. We don't need shared constraints, right?
No, this is a generic QVI. So all of the coupled information is encoded within this map. Sorry. Okay. Questions? Okay. Now, next what I want to do is think a little more about a very specific subclass of these games where you have shared constraints. Okay, and why are shared constraints relevant? Let me give you some intuition for this. So in the context of generalized Nash games, often what you have, so even in this case when I wrote it, This is actually a shared constraint because this is a common G. If I had a GI, it would be non-shared. Okay. If it's GI, then that function is idiosyncratic to that agent, but it need not be, right? It could be a general G. And so let's, and when is that relevant? Well, it's relevant in most networked regimes. So if you have a network and players are, or agents are sharing resources on that network, the network constraints that are induced on each player's feasibility set should be identical, right? Because the network that you see and network I see is similar, right? Now, we have to be a little careful. Sometimes what happens is you operate on certain parts of the network, but you could, so often in a model you might say, well, I have generation resources at nodes 1 and 2. You have generation resources at nodes 5, 7, and 8. So do you see the same network constraints as I do? How would you answer that? How would you capture the fact that if you're trying to model generators, right, and you've got a, like the network we had yesterday, you had 6 nodes or whatever it was, 5 nodes, I don't know, and firms have generation resources at different nodes, and they needn't be all the nodes, right? So it seems like you should see different constraints, but why is it that can be viewed as a shared constraint game? The LMP is just a way to assess the sensitivity of the cost to changing resource, right? The LMP is just it basically captures that sensitivity, right? But here I'm asking you, if you only have generation resources, so if you have a firm, suppose you have a network like this. So suppose I have a network like this. Okay, this is 1, 2, 3, 4. Okay, I don't know, maybe you have something like this, maybe you have some loops going or whatever. Now, agent 1 has generation resources here, agent 2 has generation resources here. Okay. Now, what happens is that when you have demand at maybe at nodes D1, D2, and D3. When you write each player's optimization problem, do you end up with shared constraints? And so you need to capture the flow.
I think we can do still shared constraints because, for example, the constraint on line from 1 to 2, it will be same, or maybe, okay, let's take different players. From 2 to 3 will be same as from 3 to 2.
So that could be mirrored, but suppose you have, so the question is that if you have a firm that only has generation resources at 1 and 2, should it be worried about 3 and 4?
I think as far as the network is concerned, the demand of the network is a common constraint for all generators.
Exactly. So what you need is that you cannot just worry about this because you need to capture the entire network. Because for you to figure out the flows are a consequence of solving the power flow equations on the entire network, right? You can't take a portion of the network and try and establish what the flows are, right? So for these types of networks, and in most network settings, if you're competing on a network, you would like to have a representation of the entire network in your optimization problem. And as soon as you do that, suppose you capture it using some sort of DC load flow model, then each player would say it's AX less than B, or AX equals, something like this, some polyhedral constraint. And in this, what's going to happen is you might say for the ith player, it might be, so this is still shared. Okay. So network constraints are often can be captured within this regime. Okay. Now, there are, so which is one reason why this framework is particularly useful. Okay. So this problem of shared constraints was first considered, or at least first seen by both Arrow and Debreu. Arrow, if you remember, won the Nobel Prize in economics, and subsequently Rosen looked at this problem in 1965, a variant of it. And in his problem, so if you see what they have is they actually have this framework where they define the problem, and in his, so I don't know whether I mentioned the diagonal street. So in Rosen's problem, they actually look at the variational equilibrium and they provide a uniqueness statement just for that variational equilibrium, which is not surprising, right? Using diagonal strict concavity, which is basically strong monotonicity of the map. Okay, so X is an equilibrium of this game. If these are just the equilibrium conditions, right? That basically my solution is always, I mean, a particular agent's best response always dominates what you would do given any other point, okay, given any other strategy. Okay. Now, there are two fundamental questions in the theory of games, and where the central concept is shared constraint games. Okay. So the first thing we should do is, what I'd like to do is rewrite that shared constraint in some algebraic form. So what you should be thinking in the context of shared constraint games is that this constraint C is going to be common to all the players. When I say common, I mean that each player is going to enforce this requirement in each of their feasible regions, okay, in each of their optimization problems. Okay. So this is a shared constraint game, and I'm going to refer to the set of C as, but C is greater than or equal to 0. So C is a concave function, so this overall set is convex. Okay, and the shared constraint, so I'm going to refer to this set as C throughout. This was script C. Now, if you look at this, I can write down, so this is important, I want to make sure everybody sees this. So if I write down each player's problem, okay, we work under the premise that this is a concave function, so the overall set is convex. Okay, so the KKT conditions of this, assuming that theta I is convex in xi given x minus I, are necessary and sufficient. And what are the KKT conditions of this? The KKT conditions of this, someone help me out? What are the KKT conditions of this? Take the gradient of the objective in xi, and what else? So what I have minus the gradient of Ci, not Ci, C, transpose lambda I, okay, and this is orthogonal to xi non-negative, and this is orthogonal to C of x. This is lambda I, okay. So when you write down the equilibrium conditions, each player is going to have her own Lagrange multiplier lambda I, which represents the dual variable corresponding to C of x non-negative. Okay. Now, in the context of shared constraint generalized Nash games, there are two types of equilibria that we examine. The first is lambda I is idiosyncratic to each player, which means that each player chooses his or her lambda I, and the second one is lambda I is common across players. And there are lots of questions here that I'm going to get into. Okay, but I want to give you a deeper understanding of the relationship between these two types of equilibria. First, we're going to define them. Okay. So before that, let me just give you a quick blurb. So if I wrote this out, let's take the case where you have idiosyncratic lambda i's. If you wrote down the optimality conditions for each player, what do you get? You get x1, x2, xn, lambda 1, lambda n, this is x1, and here you have c of x, and you have it replicated. Okay. Okay. Now, if you took the Jacobian of this map, here's what you get. Here's what you get. You get essentially, you're going to get the f of x, which captures, sorry, the Jacobian of f, which captures, actually I should know, you have to get the Hessian of the Lagrangian here. So you're going to get, okay, I'm just going to call this h of x lambda. So what is h of x lambda? I'll tell you what the first element is. When you take the Jacobian of this, what you're going to get is theta 1 of x minus lambda 1 I. So this is the Hessian of this. C1 x, sorry, xi, the ith component. Because we have a vector function, you have to take the Hessian of each component, okay? And you're weighting it by the ith component of the first Lagrange multiplier. So that's the first element. Then if you go to the next one, you're going to get cross terms. So this h of x lambda is just going to be, it's going to be it's going to be akin to the Hessian of the Lagrangian, okay? What you're going to see on the side here is actually interesting. So what you're going to see here is when you take the gradient of this with respect to each of the lambdas, you're going to see this, right? So this is going to be, transpose. Okay, transpose. Okay. And now, if you look at this, what's going to happen is when you look at, you take the Jacobian of this, you're going to get the full Jacobian. So you're going to get x1 c of x, xn c of x, x1 c of x, xn c of x. Okay. So you can see what's different. The diagonal elements of this are going to show up here, and the off diagonals won't show up. So first of all, my question is, if I tell you h of x lambda is, let's assume for the time being it's symmetric, and it's not actually. The problem is that this is not even skew symmetric, because what's going to happen is that you only had this diagonal plus something else, and this something else proves fatal. Okay, so when you're analyzing this system, it really kind of, you have to deal with this off diagonal part. It shows up whenever you analyze existence, for instance. When you analyze existence, what happens? Remember what we did yesterday? When we tried to compute, say, an x ref and a lambda ref such that this complementarity map satisfies some sort of coercivity property, we were able to get rid of these two parts because they're skew symmetric. Here I can't do that because I have this off diagonal part, right, which proves to be particularly debilitating. It's just hard to deal with. Okay. Now, what happens if I don't have that? What happens if I had a single multiplier? So then the other thing that you want to notice in this is that if you look at this system, right? If you look at this system in some sense on this side, you have identical constraints. Okay? So it's a cause for, it's an immediate indication that something awry is going to occur. Now, when you have a single multiplier, what you have is the following. So you have a single lambda. Everybody looks for a solution with the same lambda. And you have one constraint for the lambda. Now, what happens if you write down the Jacobian of this map? Then you get you're going to get again the hx lambda. But remember, this hx lambda is different. In this one, you have hx lambda 1 to lambda n. Here is just h of x lambda. You're going to get the Jacobian of c of x and negative Jacobian c of x. And now this is skew symmetric. Okay? So, and you can imagine that's one of the reasons, structurally this is a much better posed problem. However, in doing so, what we've done is we've gotten rid of a host of equilibria that might emerge in the case where the multipliers are not shared. Okay? And that's one of the issues, right? So there are several questions that emerge. Equilibria that correspond to this problem are often referred to as variational equilibria. And the reason why they're called variational, or at least that's one possible reason, is that this problem can be viewed as the complementarity conditions associated with, you know, a standard pure strategy Nash game with this constraint outside. So you can actually look at this as a variational inequality. Right? I mean, this is no different. If I told you that this was, well, I'll make it more clear as we proceed. But you can see that there's a much nicer structure. But let's continue. I'll show you what I mean.
Sorry. So in VI, we said if it's symmetric, we have an equivalent optimization. Do we have such a similar statement here?
Yeah. So here, that's one of the. So I was going to get into the integrability notion. So if you look at h of x lambda, if h of x lambda happens to be so don't take h of x lambda, just look at this problem. When you write this out, it's not particularly difficult for you to see that if this map is integrable, and I'm not talking about this part, okay? I'm talking only about the theta part.
The h part.
Well, the h actually will now have the information from the Hessians.
Yeah.
But if you look at this part, and this part is integrable, and what I mean by that is that there corresponds a single optimization, a single function whose Hessian gives you exactly the Jacobian of that part, then I think I know that you'll be able to get one.
You know what, sorry?
I know that I'll be able to construct a single optimization problem because the rest of this is skew symmetric, so we are fine. Sorry. Okay. So, but I don't, in general, I don't know that, of course, but if I can,
Okay,
yeah.
generic G and E, even without shared constraint, if we have this structure, can we have the same statement saying that, okay, if H is integrable?
Yeah, so I think you have to be a little careful about how you write that because the thing is that, because now you have the lambdas, and I think you should be able to, so that's why I want to, when I say that, what I want to focus on is this part, because this, you can see this part actually only comes from a single constraint. So I'm certain that it shouldn't complicate matters. But I don't want to call this whole thing integrable. What I'd want to do is call this part, that part of the game, because this part, if you think about it, comes from the constraint structure. You're always going to get that skew symmetric structure. But what it does is, because I was putting the wire in. So maybe we can do a quick example that might convey these things a little better. So let's take a simple example and check for integrability. So suppose I gave you this problem, minimize Ci of x, the usual Cournot problem, times xi, and let's just assume that we have summation of xi is less than c, b, xi is non-negative. Okay, and let's assume that we have shared constraints. Okay, so then what you have is you have x1 is orthogonal to, let's just assume this is Ci of xi. So it's a linear cost. So you get, this is going to be b I plus E transpose times x minus, so this is going to be, this is E transpose, this is E, this is lambda times E, no, plus lambda times E, yeah, plus lambda times E, and this is lambda times minus E transpose x plus minus E transpose x plus b. Okay, so this is equivalent to 0 is less than x lambda I plus E transpose E minus E transpose x lambda. There should be a plus C minus A. C minus AE B. There shouldn't be the same B, right? There should be some D greater than or equal to 0. Okay. Now this problem. So the question is that this problem, now you can see what you have is, now remember in this particular case what happens is that the constraints are linear. So you write down this block, the constraint information doesn't show up because it's only it's an affine function. So now even if it's a twice differentiable function, what will happen is you'll get a constant function there, some Hessian or something of that sort. And what you'll be able to write is the following. I've not done this part before, but it seems like it should work. So what you should get is minimize half x transpose I plus E transpose x plus C minus AE transpose x subject to minus E transpose x is less than B, x non-negative. So you write down the KKT conditions, you'll get a plus E times lambda and minus E transpose x. Now suppose we made the problem a little more complicated, and instead of this I had a g of x here, then what's going to happen is here I would have got a Hessian of g. If I have a Hessian of g showing up there, then I could have had the g here, because that would just be the Hessian of the Lagrangian. So I think yes, absolutely. Okay, but I hadn't done, I hadn't checked it before, but it seems like it should be pretty straightforward. So then, what I want to do now is give you a geometric understanding. Often we just go through the algebra, but it's important that you see the geometry. So suppose we go back to this, to the shared constraint game, to the coupled constraint game. Remember what I told you. Ki of x minus I, in this case, this set valued map has a very precise structure. And the structure is that yi x minus I has to lie in some common set C. Okay? And kx is the Cartesian product of these set valued maps. Now, this game is closed. Let's call this game G script. And let's assume C is a closed and convex set with a non-empty interior. Okay. Now, I'm going to assume that Ki, this is closed, convex valued, and the graph of Ki is C. Okay. So let's see what this looks like. Okay. I want to make sure that everybody sees what this looks like. So what is, if you're, so let's see what this is, right? So if you're here, this is, let's take a two-player game. Okay. And let's take strategies x1, x2. If your strategy is x1, suppose your strategy is x1, then what happens is the feasible region that is induced. Now remember, and let's assume that so we're taking a point x1, x2. Okay, but now look at x1, x2. x1, so if this is x1, x2, there's an x, but this x doesn't lie in C. Okay. But anyway, bear with me for the time being. So if I have a decision x1, then the set induced for player 2 is k2 of x1. Okay, so that's his feasible region, that's her feasible region. So if player 2 makes a decision x2, the set induces k1 of x2. Okay. Now, if you look at the Cartesian product of that, that's the set. So for a particular x, that's the set. Remember, when you have a Cartesian product, you get a rectangle. But these rectangles keep moving in this case. And the reason they keep moving is because they're parameterized by an x. Right? So for every choice of x, this rectangle shifts. Okay? Now let's take the case where the set, so look here, the set x, the decision x, the tuple of decisions x1, x2 did not lie in C. It needed to lie in C, right? That was our point, that x1, x2 have to satisfy this constraint. That's like saying C of x1, x2 is non-negative, right? That's not the case there in the first picture. Let's take the case where x1, x2 do indeed lie in C. Okay, so it lies in C. Now here's what happens. When it lies in C, this is what K of x looks like. Okay. That's it. Okay. And I've looked at another instance there. So if I took the x inside, you find that this K of x might extend over. Okay. Now, so that's the geometric understanding, that basically the set, the shared constraint may be some closed and convex set like a ball or an ellipse, but the set that is induced, the K of x is always Cartesian, so that's going to be a rectangular set. Now you might say, is K1 of x2 just a line? No, it's not necessarily a line. It was just that in this case it's a two-dimensional problem. It's the Cartesian product of sets. So if you look at K1, x2 and imagine that in the space of x1 this is a set. Could be some polyhedral set, and that's another polyhedral set. So you have a Cartesian product of two polyhedral sets. Okay, so the rectangle is supposed to embody the Cartesian product structure, not the fact that each of the sets is just a line. That of course might work in a very simple setting. Right? Does everybody see this? This is meant to represent and motivate, but not to suggest that x1's feasible decisions are on this line. That's not That's true for this simple problem, but in general not true, right? Okay, so now, so in general, a strategy tuple x1 to xn, just to remind you, is a generalized Nash equilibrium if xi lies in the solution set of ai of x minus I. This is ai of x minus I. Okay. Now, if I take the mapping f as the concatenated gradient map, which is our standard approach, a GNE solves this quasi-variational inequality. Okay, we just said that. A related variational inequality is the following. So, this is the variational inequality corresponding to f of x transpose y minus x is non-negative for all y in C, a constant set. Let's make sure everybody understands. In this case, look, this is k of x, this is C. Okay? The QVI requires that I satisfy the variational conditions for every y in kx, okay, and I want x to be a fixed point of k of x, I mean of k, which means x has to lie in k of x. The VI, this is a different problem. Find x in C such that this holds. This is just a standard variational inequality problem, VI C comma F. Okay. It turns out that a strategy tuple is a variational equilibrium of G if x is a solution of VI CF. So, if I want a solution to the generalized Nash game, an equilibrium, a simple equilibrium, not a simple, an equilibrium is available by solving a variational inequality, and thus the term variational equilibrium, because it comes from a variational inequality. Okay, so here's what we've tried to state. We have a shared constraint Nash game. An equilibrium corresponding to the shared constraint Nash game satisfies this QVI. Okay? So, X is an equilibrium of the generalized Nash game, or we'll just say X is a GNE if and only if x is a solution to QVI x comma f. Okay, this is if and only if x is a VE if and only if x is a solution to VI C comma f. Okay. Now, the first claim is if x is a VE implies x is a GNE. So, you can get a generalized Nash equilibrium of a very specific variety by solving a variational inequality problem. Okay. Now, let me ask you a question.
Sorry, C. I mean,
C is the set that you give.
Is it smaller than or more compact than original X, or?
So, the original X is a set valued map, so its image keeps changing, right? So, as I said here, if X is here, this is K of X, this is C, right? If I move X, it changes. If I move X out, it could be here, right? That's, in some ways, it's hard to get an understanding of, because K of X keeps moving everywhere, right? And it's not necessarily that's inside it, outside it, you know, it's not clear. But in some sense, it's less relevant for us. What is relevant for us is that this convex set provides us with one solution to the variational to the generalized Nash game. Now, let me ask you a question, and that's going to motivate the next 10 or 15 minutes. If you solve the variational equilibrium, you get a solution to the generalized Nash game, or an equilibrium of the generalized Nash game. Suppose it turns out that no equilibrium exists to the variational inequality. Does it mean there's no equilibrium for the generalized Nash game? Because what I've done is I've said I'm going to keep it. Okay. I've said if this is the set of solutions of the GNE, I have a set of solutions of the VE. And I get this and I say, oh, it lies inside this. But do we know if this is all, if I tell you this is non-empty, is this always non-empty? We don't know that, right? So that's what we focused on in one of our papers, because that question is important, right? If somebody directly says, let me ignore the GNE, let me always solve the VE, right? And it turns out you can't solve it. Can you directly conclude that the GNE has no solution? If you could, that would be great, right? Because then it says that the original problem is not solvable. The problem becomes if you can't solve the VE and the GNE does have a solution, right? So that comes under an economic paradigm called refinement of Nash equilibria. So there are these notions of refinement. So what is a refinement of a Nash equilibrium? It means that when the original set is empty, this set is also empty. Okay, and if the original set is non-empty, this set better be non-empty. Okay, so the point is that you can always refine it and focus on the smaller set, right? So I'm going to study VE as a refinement in an effort to give you a deeper understanding of the role of the variational equilibrium, right? So the refinement of the set of equilibria of a game is a subset satisfying a certain rule, where this rule has a property that any game with a non-empty set of equilibria also possesses an equilibrium satisfying this rule. Okay, and there are a host of these, right? Meyerson, as you might know, won the Nobel for mechanism design, but he provided a refinement called proper equilibrium. Okay, there's something that Selton also, I think, won the Nobel. I'm not quite sure if Selton, but he may have, and he suggested something called the trembling hand perfect equilibrium. Okay, so there are a host of these different types of equilibria that emerge. Okay, and this I think is in the context of matrix games, if I remember correctly. Okay, and so our question is the variational equilibrium a refinement of the generalized Nash equilibrium? And if so, under what conditions? Right? I mean, whenever we do something, we need conditions. Right? So, what do we know about the VE? We know that every VE is a GNE, right? The solution of the variational inequality problem always lies in the solution set of the QVI, because every VE is a GNE. Why is that? Because if you get me a VE, then I know that I can just replicate each of the lambdas as lambda i's, and I'm able to get a solution to the original by just setting lambda I equals lambda. To show that VE is a refinement of the GNE, I need to go in the other direction. I need to show that when the solution set of the QVI is non-empty, the solution set of the VI is non-empty. So it's a subtle question, right? It's a subtle question, but it's an important one. Okay, and it's also important because people routinely will use the VE as a proxy. So you have to have an understanding regarding when this proxy is indeed available. Because if the proxy were not available and you were to mistakenly assume or conclude that the GNE does not have a solution, then that's problematic. Well, that can't happen. So for instance, if this is so.
Uday, can I ask you a question?
No.
But GNE may have multiple solutions.
Could have,
VE
yeah.
is one of them.
VE is one, but VE could also have multiple solutions.
Yeah. So why we are interested to solve VE?
The reason why we're interested to solve the VE is because of the fact that the VE is tractable. The VE requires you to solve a single variational inequality problem, and that variational inequality problem is, by definition, you solve a variational inequality problem, and and we have a much better understanding of solving those, right? We have, and we can leverage the monotonicity of the map to construct algorithms. There's lots that is known. I should say for QVIs, for the folks in Louvain, Yuri Nesterov has. I mean, there are other algorithms for QVIs, but there is one that he produced which is for a very restrictive class of QVIs, but still an algorithm that uses projections. So what I was saying was this: if the solution set of the QVI x comma f is not empty, can I prove the solution set of the QVI of the VI of CF is not empty. Right? So if this is non-empty, this is non-empty. What is the negation of this? The negation of this is that if it turns out that I try and solve the VI and this I find there's no solution, then I can directly claim that the QVI doesn't have a solution. And why is this important? This is important because it gives you an oracle to test whether the generalized Nash game has an equilibrium, right? It immediately tells you that if I want to ascertain if the generalized Nash game does not have an equilibrium, just check if this. In general, we didn't know that. We just said, oh, this is a point in the set of equilibria. Nobody quite understood what happens if you can't find such an equilibrium. But this gives you a test, and we often need these types of tests to understand the well-posedness of market structures. Okay?
But you gave us some two simple propositions in slide 4 and 5 that we can check if the solution exists for G anywhere.
But it's the hard ones to check, right? You have to check the set valued map. This is a cheap one, right? All I do, because even for me to check this, right? If checking this in some sense is not easy, right? One thing you could you can run an algorithm, and if it turns out that the algorithm is just a constructive scheme, if it turns out that the problem is strongly monotone, we know an equilibrium exists. So this will never happen. If the problem is monotone, like the problem I gave you where e raised to minus x, we know there are some settings where you don't have an equilibrium. Suppose you run the scheme, you find that you don't get a solution. Then you start analyzing, and it turns out you can prove, and you can often do this. Like we've done this for some other problem with uplift, where we were able to show that pure strategy Nash equilibria for marginal cost pricing with commitment decisions do not exist. Right? But that was an alternative avenue to prove that. But if we were to prove it, you could directly claim something for the more general problem. Okay, it gives you the handle to do that. Okay, now, just give me a few more minutes. I just want to get through this. Okay, so suppose C script is given by the set of x such as C of x is non-negative. C is a continuously differentiable function, and x is a GNE if these KKT conditions are satisfied. Look at these KKT conditions. These are the non-shared multipliers. And the V with shared multipliers requires that lambda I is equal to lambda j for all ij. Okay. Now remember what the geometric characterization is. If x is on the boundary of the set, then x is a solution to Vi xf is if negative f lies in the normal cone of C, of x comma C. Right? And x is a solution to QVI kf if negative f lies on a normal cone of x comma kx. Okay, these are both normal cones. You just need to make sure that x lies. So in some sense, x has to lie. So each of them characterizes the optimality conditions of, or the equilibrium conditions of the associated variational inequality or quasi-variational inequality. Okay. Now, why is it that we might be interested apart from the reason that it's tractable? Here's some other ways to think about this. Often games admit a large number of GNEs. They might have manifolds, right? So for a modeler, the GNE by itself provides no clarity about the outcome of the game, right? So suppose I had this example where I said x is equal to alpha and everybody has their own associated multipliers. Then the KKT conditions for characterizing this game are x, just you write down the optimality conditions, it's xi, L of x star, x star, L of x star. If it's a univariate function, you just take the gradient of that. That's equal to lambda I. That's the KKT condition. Right? Now, and now you can see every point in this set, you can see that every point in this set, x equal to alpha is a GNE of this game. Right? So the question is, there an equilibrium which is better than the others? Better in some quote unquote. And what way? What is the notion of better here? Right? So let's consider a game that appears in communication networks called a bandwidth sharing game. And this is also relevant to the context of solving problems in the context of power markets, where the Lagrange multipliers can be interpreted as the price charged by either the administrator, the grid operator, or whatever, right? Now, sorry, the equilibrium with non-shared multipliers is an equilibrium that results from discriminatory prices, right? Because you have differential prices, right? So it can be viewed as such that if you try to implement it, each player is going to see this as a different price that is imposed by the system operator. But often the situation modeled makes it unrealistic for the administrator to be able to distinguish between various users. And if you were to implement the equilibrium, you have to have consistent prices for a variety of other reasons, right? You cannot have different LMPs at the same node for different users. Okay? So the V in that context is the right equilibrium. It's the implementable equilibrium, and it allows for charging in this context a uniform price across all users. Right? But a natural question is, does the V always exist given that you have a generalized Nash game? Right? If the V is a refinement of the generalized Nash equilibrium, then an equilibrium with discriminatory prices exists if and only if the one with discriminatory uniform prices exists. So if this one doesn't exist, this one doesn't exist. Okay? Question?
Can you call it better equilibrium?
No, I call it. I'm only calling it better, or I'm not really. I don't want to use the term better. I think it's appropriate in some contexts. It's appropriate in the context when the multiplier can be viewed as a vehicle for providing resources to users, and you want to be fair about how you provide those resources. So if it's a price, the price is used to provide resource to the users, right? Revenue or whatever. And so if you have different prices, you get different. For the same contribution, you get different revenues. So from that standpoint, it's fair. I don't want to say better. Maybe the appropriate term should be fair. Okay. So now imagine a game for which we know a GNE exists. So this motivation is from the standpoint of fairness. The second motivation is from the standpoint of computation, right? And which I believe is also quite important. It's pointless having something which is where the computation of the object is so hard that it makes it kind of useless. So GNE is hard to compute since it involves the solution of a QVI. The solution, as I mentioned to you, a QVI requires you to find a fixed point of this map x of x, or of this mapping x, such that it satisfies that variational inequality, that associated inequality. A V is comparatively easy, right? And so the role of the refinement is that, for us to know that the existence of a GNE is sufficient for the existence of a VE. Okay. So computation of GNEs has often been restricted to classes of games for which one can claim the existence of a V independently of the existence of a GNE. So generally in the past, before we did this kind of research, the reason why I bring it up is because I think it's important for us to collectively understand why we use the V, right? People just blindly use the V. We need to understand why and what the relevance of the VE is with respect to the GNE. Okay? In the past, people would just use the V, regardless of whether they knew anything about the original problem. Okay? So is there a class of games, S prime, with properties weaker than these that are not by themselves sufficient for the existence of a V? So for instance, if I gave you a problem for which we had existence of the VE because of compactness, then I can directly claim something about the existence of a G, right? But can we get properties that are weaker such that by themselves it's not sufficient for the existence of a V? For instance, if I told you the mapping is just monotone and the set is just closed and convex, and that's not enough for us. Right? We don't know if a VE exists. What we do know is that if there were conditions under which the VE existed, then we could then say something about the existence of the GNE. Right? Okay. Now the implication that this is non-empty implies that the VI does not hold for all F and C. Okay, this is something that we can. So we'd like to if this is non-empty implies that this is non-empty. The other way always holds, right? If the VE has a solution, the GNE there is a GNE, because constructively we've got a GNE, right? This relationship doesn't hold in general. What we were able to prove is that it holds under some conditions, right? When does this implication hold? Are there games other than those in S satisfying the above? And is there a unifying criterion that can identify these games, right? So there are such games with monotone maps and some appropriate properties of the recession cone. And how do we prove this statement? This statement is not that easy to prove. So this was our first instance of trying to use degree theory to show an implication rather than to show a direct existence statement, right? So the way we show that is the degree of something is non-zero, some other degree has to be non-zero. Okay, so we use it to relate to different sets of games.